That's on. Is it on? Maybe not. Can you hear me?
Yes, I can hear you.
Okay. All right.
All right, so let's continue for those of us who are part of the workshop. So for those of us who are not part of the workshop, I just want to mention that this lecture is part of the activity we had here at DIAS this entire week, and it's devoted to mathematics and computer science. And Louis Kauffman, who is our next and last speaker for the workshop, kindly agreed to give a broader talk with less perhaps technical details and more vision and perspective. And Louis is the right person to do so, since he's one of the founding fathers of field quantum topology. He is known for Kauffman bracket, Kauffman polynomial, and many other exciting things. In the same time, he has strong connections to computers and has served as president of American Mathematical Society for Cybernetics, and has many awards in this regard. So without further ado, it's my pleasure to introduce to you Louis Kauffman, and so let's welcome him.
Thank you, Sergey, and thank you for inviting me. This talk is going to have a lot of visual material in it, and maybe some technicality, so I hope you don't mind it being a bit bumpy in that way. But well, let's begin with the following. Let's see if this is going to work. Yeah, okay, there. Here's a typical problem in knot theory. Is this knot knotted? You can see it. Oh, good. Okay. So, what do you think? Being knotted means that there's no way to move it without crossing itself or cutting it and get it straightened out into a nice circle. It's hard to tell. That's the thing about this particular aspect of topology. It's just hard to tell. But there are ways to cajole a computer into taking a look at such a thing. And let me show you something about that. There we go. There it is again. The same object that you were just looking at, and now we can rotate it around and take a better look, but it's still not obvious whether it's knotted or not, unless you happen to have maybe the right brand of intuition, and you would find out that in fact it's unknotted. But what this program is going to do, the program is due to Rob Sherine. It's called Knotplot, and it's commercially available, and it's not too expensive if you care to if you care to fiddle with this. So it was unknotted. Of course, to get it to a nice round circle is going to take longer. But what's going on here is that the knot is coated with electrical charge, quasi-electrical charge or pseudo-electrical charge, and it's self-repelling itself. So in other words, what you're actually looking at here is a set of points in three-dimensional space. And they're in a cyclic order. And so the data that this program gets is a collection of points. And then if you take a pair of these points, then you can set a force between them, repulsive force. In the case of the program, 1 over r to the 5th turns out to be better than 1 over r squared for doing the kind of experiments you want to do. And there also are spring forces between adjacent points that pull at them, and they can be adjusted. So then you might wonder, well, maybe this is a good way, this field theoretic way of doing it, to tell whether a knot is knotted or not, is that maybe this will always unknot knots. But you should be skeptical about such things. And the first part of this is going to show you some examples where it becomes very hard for a program of this kind to do it. So let me show you the kind of example I have in mind. I'm going to make one. If I can see what I'm doing. Yeah. Okay, so I made a gadget. Now, if you look at this gadget a little bit, you'll see how it's made. You start by twisting some rope like this, and then you have 4 ends. And then you take the bottom 2 ends and you twist them this way. And then you take the right hand ends and you twist them this way. In this case, I did 5, then I did 4, 3, and 2, like that. And then I have another one over to the right, where all the twistings are the negatives of the ones in the other one, and I don't have all of them. In the one on the right, I have 1, 2, 3, 4, 5, and in the one on the left, and the one on the left, and in the one on the right, I have 1, 2, 3, 4. Okay, and then if you put them together, and I've put them together in the following way: box with some ends attached to it, next to a box with ends attached to it, and then the ends are attached to one another on the inside, and they're attached to one another on the outside. You'll see this better if I just run the program for a moment. So you see how it's connected across the top and it's connected on the inside. Well, that negative clump on my right and the positive clump on the left actually can cancel each other out and undo one another, and this is unknotted. I'll try that. Let's see. Well, that's just a way of pointing at that thing, but okay, fine. Let's see what happens. So we want to, so I want to show you that the program is going to unknot this. It will. Now we'll get it started for stability's sake, and then let it go faster by allowing the springs to act. That perturbs it more, and the whole thing will go more quickly. And I was fairly confident. Oh, yeah, thank you. I was fairly confident that this one would actually unknot. They don't always unknot. If you make this kind of an example a little more complicated, it's going to have trouble unknotting, but this one is succeeding, as you see. What has to happen in this kind of an example, apparently, is that it has to untwist. And then having untwisted, it can untwist some more, and having untwisted, it can untwist some more. And if I make this into a recursive situation like that, and make more and more and more of them, more and more terms, then it doesn't find it so easy to undo, but it's succeeding here. Let's just let it run for another moment or two. I think you'll agree that it's doing its job now. There's a little bit of twist left, but not much. And there you are. Now let's look at let's look at another example of this. So I just created this file beforehand so that it would be reliable. So what I have here is just using one. So I twist by one, and then I twist by one, and then I twist by one, and I twist by one, and I do that for a long time. And then I have minus ones over there on the other side, and these two clumps are going to cancel each other if this clump on the left could rotate enough to go through. And this one will succeed. I'm using 10 and 9. As I said, I need one less on the one on the right in order to be sure that it's unknotted. So we'll let the springs work. And the last time I tried this, it did unknot. If I go one step further, I know it won't. It's possible that I am not going to get it to unknot here either, because the initial conditions are varying a little bit as to when I start doing it with the springs. Oh, it's entirely possible this one isn't going to unknot. This is right on the edge. I know that if I did 11 and 10, it definitely won't unknot, no matter what I do. But now you see the problem. Yeah. I'm sorry. At what point does the program know that the program, of course, never knows whether it's unknotted or not. It knows nothing other than the dynamics that it's going through. We're observing the program, and what I observe when I look at examples of this type is that, of course, sooner or later you get to a situation where it would unknot if a certain curve, that kind of curve going around the middle, if that could slide up over that clump and come back around, if it could. You saw it do that kind of thing in the previous example. If it could, then it's down one step in that recursive stack of things, and it will just go ahead and unknot. But if that belt in the middle gets stuck in the middle, then we could leave it running for the next week and it won't do anything. It'll just hang in there that way. And if you make the examples, this example was right on the edge, so it's amusing to see that I tried it this morning before giving the talk, and it unknotted it, but now it's not doing it. Okay, but if I give it one step more, or if I gave it a very large example like 100 ones and 99 ones, then it definitely won't unknot it. This program won't. Of course, you can do perturbations, but I'm asking the question whether with just this slight amount of perturbation and the forces, whether it would unknot it. If we don't, it'll have more trouble unknotting it if it's just the forces and no spring perturbations. So this class of examples can always be made more complicated, and I have found that I can always make things that the computer will not unknot by doing this. Now, to have a good analytical theory of what's going on here is another matter, of course. It's very interesting to see what, as long as we're talking about it, maybe another example is worth doing. You can take a standard kind of knot.
Maybe a knot that a human could do quickly.
I'm sorry.
Maybe a knot that a human could do quickly.
Well, what I'm doing here is taking a torus knot of type 5-3. Okay, it lives on the surface of a torus. Maybe I should start it again and stop this. Oh, sorry. There. So the beginning of this is a bit flat form of a drawing. It's clearly on this. It's clearly going around a torus knot of type 5-3. And then what will happen when this self-repels? And it will self-repel into another form. And it's very interesting to take a knot. I just chose that torus knot. It's very interesting to take a knot and find out what kind of geometric form it will end up in. And again, one doesn't have much analytical grasp of this sort of thing, but one can do experiments and see what sort of forms you're getting. So these are computer experiments which are certainly worth thinking about. I'll show you one more bit of phenomena here. I'm sorry.
People interested in protein folding, pay attention to this type of
I didn't quite get
in the problems of protein folding.
a protein folding.
It looks very
Yeah, of course, protein folding is a somewhat different situation, but their knots do occur in protein folding. And then in protein folding, you have situations where bindings occur as the thing folds. And it's not obvious yet to people why knots are necessarily occurring in protein folding. There's some energetic reason why it's better to have knots than not to have knots in certain situations. But as you see here, you get somebody which is beginning to stabilize in a certain form, right? I chose this one because just randomly. I want to show you a simpler one, and then you'll see the kind of phenomena that might occur here, but I'm not going to risk it. Let me take a torus knot of type 3-2. That's just an ordinary trefoil knot. It's a knot which is going 3 times around the torus one way and twice the other way. And if we run this, it floats out into this position, which looks like a couple of ears perpendicular to one another, and pretty much stabilizes in that form. That's not the way you usually think of a trefoil knot. If I said to you, there's a rope in my pocket, but there's also wires and things, so I won't grab it. But if you had a piece of rope and you wanted to make a minimal trefoil knot, why, it would just look like that, a small item. This isn't seeming to do that. So what's going on here? If you if you look at the energy that corresponds to the inverse, the sum of the inverse distances between all the points, you could think of that as an energy for the knot. You'll get a certain energy for this. I won't bother you with the numbers. And then when I perturb it, and I'm now about to perturb it by letting the springs act. So there are springs in there, and they start, and it goes into unstable oscillation and falls into the lower energy level. Now there's a lot of kinetic energy in there because the energy went into the spring motion, and then the program lets me drain the energy out, the kinetic energy out, and I end up with something that definitely looks like what you would have thought would have been a minimal energy form for the trefoil knot. So that means that that you're going to find that things go down these gradients to some stable positions or semi-stable positions and then hang there. And then if you perturb it some, they could go down farther. But the kind of example that I was showing you a few minutes ago will take a lot of perturbation in order to get any farther down. You'll have to grab a loop and pull it around something. So it's not a gift that will unknot all knots for you. But the question is, how much unknotting can it do, and how much distancing between knots will this kind of dynamics actually hold? So that's a very interesting question, I think. And I'm going to skip to the next topic, but go ahead.
If you perturb it, does it always then go down to a lower energy situation?
Well, if you perturb it sufficiently, you could unknot something that was unknotted, because after all, if you have an unknotted curve, what you do when you grab hold of it and pull it around is perturbing it. But what you saw in my example, the one that didn't unknot, is that the slight perturbation of the springs wasn't enough. And it was clear that you'd have to go in there and intervene in a strong way in order to get something else to happen.
Thank you.
So if you would like the field to somehow automatically unknot the knot, it's not happening in general. Yeah.
So do these stable or these metastable configurations depend on the kind of potential you have between these particles, or it is just geometric?
I'm not sure I understood the question.
Do these stable or metastable configurations that you have of these knots, do they
Yeah.
depend on the kind of forces there are between particles that you showed before, or they are independent of these
you
forces?
would like to think of it as forces between particles. Is that what you're saying? Yeah, maybe. Maybe. There are others. There are some speculations, for example, that that glue balls could be knotted in elementary particle physics. And a glue ball is the result of a cork string that annihilates the ends. And so you have gluon field in a knotted, possibly knotted form. Or you could put other kinds of forces between the particles that the knot is made up of and do other experiments, of course. So there's certainly room for lots of variation there. So let me leave that topic unless you have another question about it.
Yeah, Lou. Does it help a lot if you embed it into high dimension? Lou here.
Where was the, yeah.
Does it help a lot if you embed this knot into like 100 dimensions instead of 3 dimensions and run physics from there? So you're running like 1 over r to the 4th power force here, right?
Yeah.
And like if you run it in 100 dimensions instead of 3 dimensions, like there potentially is more space to
you want to run
maneuver.
it in higher dimensions?
Yeah, like just embed it.
Sure, you could.
But
And you could still look at the knotting phenomena. Knotting phenomena will be codimension 2 most of the time in higher dimensions. That's the kind of knotting phenomena you're going to be interested in. Surfaces in 4 space, right?
sure, but the physics could be.
Or 3 manifolds in 5 space, but surfaces in 4 space is a viable notion. Think about.
That's right. Like I understand topologically, it's fine to reduce to 4 dimensions, but like from a physical perspective, like there could be entirely new dynamics in 100 dimension or 1000 dimension. Like I'm wondering if you run the dynamics in a higher dimension, do you expect to see better unknottedness?
But are you hoping to think about one-dimensional things in higher dimension?
Yeah, just embed this. This is a circle embedded in R3. Just embed it in R100. You get some.
Well, but you know that if it's embedded if you embed a one-dimensional curve in higher dimensions, then it will unknot.
Yeah.
Right. If you think of this nice knot in 3 space and think of it as sitting inside of 4 space, then you can take an arc of it in 3 space and move it up near the other arc, and then it just jumps over using the 4th dimension and ends up underneath. And so you
Right,
can do
so
a knotting
I
operation.
guess maybe like the relevant question here is if you embed the 3 sphere into the higher dimension, like essentially I'm trying to change the physics here. I guess maybe that's another way of thinking about it.
But still, you could ask, if you did have it partially embedded in higher dimensions and you wanted to see how fast it would unknot, then
Yep.
there would be some quasi-physical process about it getting near to itself and allowing itself to leap into 4 dimensions and come back on the other
Well,
side.
I guess like the point here is that like you're gonna embed the 3 sphere in a higher dimension as well. Like the 3 sphere that this guy
Yeah,
lives in.
yeah.
Right. So you don't have this like trivial phenomenon.
So, and ostensibly here, we're just working in 3 space, but we could work in 4 space.
Yeah, so I'm just okay. I mean, I'm just wondering if the physical process would be quite different.
Yeah,
Like,
in
you can
fact,
expect better.
I'll be talking about something quasi 4-dimensional in a moment.
Okay, great.
Okay. Okay, so now I want to talk about knotted vortices. And this is an old topic which people have been speculating about for a long time. Kelvin Thompson, back in the 1800s, had a theory that atoms were knotted vortices in the luminiferous ether. And so that's an early string theory, if you like, phenomenological and 3-dimensional. The idea that the atoms were somehow knotted vortices in the ether. And he drew pictures of what he thought they looked like. And it was a popular theory. And whoops, I'm going backwards here. And other people who were mystically inclined thought about those knots as somehow the harbingers of materiality coming out of spirituality, and they drew pictures, and it was a very popular theory. But it disappeared after a while because the ether was not thought of anymore as a fluid, and the Michelson-Morley experiment made it hard to think about the ether altogether. And so the idea of knots as fundamental to physics in the way that Kelvin wanted it disappeared. Also, Kelvin and his people, they never saw a knotted vortex. And neither did Herbert Jela here, who was writing in 1971 and theorizing very much like Kelvin. He had the idea that elementary particles were quantized knotted flux. And he drew many beautiful pictures of these. So here's a neutrino and an anti-neutrino and so on. But then in 2012, Kleckner and Irvine at the University of Chicago figured out how to actually produce knotted vortices in water. So that changes the game. You actually do have knotted vortices somewhere that you could look at. And how did they do that? Well, you could make an ordinary 1-dimensional ring vortex by using this method. You take your lips and you blow the smoke across it, right? And you get a vortex. Well, this is the analog of lips, this little template. Its cross section is a teardrop like that, so that you'll get vorticity off the edge if you moved it quickly through the water, or you blew the water through the ring. But their method is to take that ring and pull it quickly down through, and then up will float this vortex. Well, if you could do it with an unknotted band like that, why not have a knotted band? And so with the help of good technology and 3D printing, they tinkered with knotted bands until they got it to work. And so they can do an experiment where they actually produce a knotted vortex, and here's some of their movies. Oh. The movie doesn't work under these circumstances, whatever they might be. Doesn't matter. You get the idea. It's going to be pulled down through, and up will come this one-dimensional vortex. And similarly here is the knotted template. It's going to be pulled down quickly, and you will get a knotted vortex like that. Sorry, I can't show you the film. Probably I can show you the film if I go elsewhere in the computer and find the films, but we'll stay with this. So the film is worth seeing, and you can probably find it on the YouTube anyway. The template pulls down, the knotted vortex floats up, and then they use high-speed photography and go round, so you can really see that it's honestly trefoil knotted vortex in there. Now, these are very unstable, and they tend to fall apart. And that's the interesting thing, the way they fall apart. They fall apart by a bit of the line vortex comes near another bit of the line vortex. It goes through a complex interaction and ends up rewriting the vortex in the opposite way. So you have two lines that are parallel, and they get cut and recombined like that, reconnected in that pattern. And this happens regularly if they get close enough to one another, and the whole thing will turn into an unknotted or unlinked configuration when it does that. So we got involved in doing some experiments with that, where the experiments are not with the water, but with a nonlinear Schrodinger equation evolution that's very well known, the Gross-Piatowski equation. And you then are looking at phase singularities for this Schrodinger equation. So there are phase angles, but along the line of the knot, there's no well-defined angle. And then the knot goes under an evolution according to that differential equation. So again, probably this movie didn't work right, but you can see some shots of what happens. So here is the trefoil knot, and then it's getting nearer and interacting with itself. And in this case, in 3 places undergoes that reconnection like that and gets unknotted. So this leads to a topological question. What's the least number of reconnections that you need to make in order to unknot a knot or a link, right? It's a nice puzzle. So let's be clear on the diagrammatic topological side, what it is we're saying. We have a vortex, which means that the fluid is turning like that around the vortex. And since the fluid has a turn direction, we can give a direction to the vortex line by the right-hand rule correspondingly. So if the fluid is turning that way on the left one, the direction on the vortex line is up. And if the fluid is turning that way on the right one, then the direction of the vortex line is down. And you see that in this configuration, the fluid flow is uniformly going through the middle part, right? So the fluids are, so you can have fluid flow going through the middle part between those lines. And that's the condition under which the reconnection can occur. So formally, reconnection occurs when you have an oriented line and another oriented line, and then you just cut that out and reconnect and rewrite it the other way, and they're still oriented, okay? Now that's called an oriented saddle point by topologists, doing an oriented saddle point on the knot. And if you're a topologist, you do tend to think of that 4-dimensionally. You think of it as an evolution that went on between, a picture I didn't draw. Oh no, I did draw it later. I won't worry you about drawing on the blackboard. But let me say what I had in mind, that I have these and they're going to undergo, I have these and they're going to undergo this, right? Now, if you think of that as happening in time, then time meaning I'm going forward, then they come forward like that. And I traced out a surface, right? In this case, one circle turned into two circles. And this is like a pair of pants, where the bottoms of the pants are near me and the other one is far away. So a saddle surface. And so in 4 dimensions, it traces out a bit of saddle surface. And then, and then you can look at different reconnections that occur and think about the surfaces that they trace out. So I'll have some drawings in a moment, but there are some simple cases of what happens here that are worth looking at. Here's a crossing in a diagram of a knot. And as you see, at one place in the at 2 places in the crossing, you have a line going in and a line going out. They're oppositely oriented. They could undergo reconnection and they could do that. Right. So over here in a trefoil knot, you could get a reconnection here. And then you would have something that was still non-trivial topologically. You have a link like this after the reconnection. And then one more reconnection over here, and it's unknotted. So it looked like the trefoil knot needs 2, because as soon as you do one, you end up with a link, and then you need to go through the other one and get it to be unlinked. Yeah.
So this reconnection that happens, does this always happen? Does it depend on the medium in which the vortex is created? Like you showed, for example, the vortices in water, and I'm thinking,
well, you're not always going to get a reconnection,
that's
but
right.
it's highly probable if two appropriately rotating bits get near one another.
But is that then a general statement? I'm thinking of early universe, of the cosmic strings, different directions. Do they come, if they come close to each other, is that always the case that they will reconnect?
Well, I'm not quite sure what you're asking. I mean, the situation is that if they were not oriented correctly, now they may. I have some other pictures of water vortices. You'd see that some interaction occurs, but they won't reconnect. If they're appropriately oriented, then they can reconnect.
It can. Okay, it's
And-
not always that they do.
Yeah.
Okay, thank you.
Right. And what makes them reconnect rather than not reconnect is a mystery to me. Okay. Now this was another experiment of this type using the knot 6-2. And it ended up like this. You started with the knot 6-2, and then it underwent a saddle point and ended up as a link. And then that link underwent another reconnection, and it ended up as a trefoil knot. So you did 2 reconnections and it landed on a trefoil knot, and then you seem to need 2 more, as we saw, in order to get the trefoil knot to undo. So does 6-2 require, 6-2 being the name of that knot over there, does it require so many reconnections in order to get unknotted? And the answer is topologically, no. Maybe in the case of the differential equations evolution, yes, but certainly not topologically, for the following kind of reason that I'll get to. This is out of order in the way I was just talking about it, but let's talk about it and then I'll come back. As I said, you trace out bits of surface, and you can think of those surfaces as being the world lines of the vortices, right? The vortex at the top consists of these 2 little line segments, and then it traced through the saddle and ended up reconnected at the bottom. So you can think of a bit of surface that's being created. And then in the general topological situation, you can also think of circles dying or circles being born. And then you can think of general surfaces that can occur between one-dimensional circle and another one-dimensional circle or circles. So those are called cobordisms. And we like to think about them in general. And we know some information that we could put back into this situation from the point of view of the topology, because we know the answers to some questions of the kind, what's the least genus in 4 space that this knot in 3 space could bound? Okay, I'll come to it in a moment. But here's our example with the trefoil knot. In the example with the trefoil knot, we went through a reconnection and ended up with these 2 circles. That's the middle schema over here. Here, I haven't drawn how they're linked over here. I'm just looking at the surface. I went through one saddle point and end up with 2 circles. And then I go through another saddle point and I end up back with 1 circle. And what happened as I generated the surfaces that I got some genus in the surface. I got a hole in the surface. Okay, so I can count how many genus, what is the genus of the surface that I get. And every time I have a hole in the surface like that, it corresponded to 2 reconnections, a saddle point at the top and a saddle point at the bottom. So here's what happened with the 6-2, as I said, but let's skip past that and look at this topological fact. Another way to simplify knots is to switch the crossing, but just switch it like that. Now you could do that continuously if you had 4 space available to you, as I was saying to Greg, because you can just move it into 4 space and put it on the other side. But we're not thinking about that here because all these things are happening in 3 space. But you can go through saddle points and end up switching the crossing. And it takes exactly 2 reconnections to switch a crossing. And I've illustrated it here. I put a little twist in, a little curl, and now I have an edge going in the opposite direction. And then I bring those 2 edges together and they go through a saddle. And now you see I have this bit of line going underneath. So I pull it back and push it back over and go through a saddle again. And I end up over here and the crossing has been switched. And what happened as far as surfaces was generated is I have 2 saddles in order in that way, and I got a bit of genus. So that can always be done in principle, in topological principle. But if you were thinking of something evolving like that differential equation, then it seems not so likely that it would know what to do to pull back and then come back over. It doesn't look energetically likely. So this might not happen. But the fact is, whoops, let's skip that. The fact is that 6-2 can be undone by switching 1 crossing right in the middle. That's a topological fact about that knot. That crossing right in the middle that I've shown you switching, the knot on the right, on the immediate right of the 6-2 is unknotted. You can visualize that one. It's not as hard as the ones we had before. You can take that arc and push it in this direction and it all comes apart. So 6-2 therefore can be undone in 2 reconnections. And I want to know how to find out what the reconnection number is for a knot or a link. So there are some lower bounds for the number of reconnections needed. And they come from thinking about things 4-dimensionally. There's something called the signature of a knot, which I think I won't bother you with, which turns out to be a lower bound. But it's something that you can compute from the knot directly. And so in the case of the trefoil knot, the absolute value of the signature is 2. And that gives a mathematical proof that the reconnection number of the trefoil knot is 2. So signature is nice, but we would be taking a certain amount of time if I were to explain to you how it's done. But it might, if you hadn't seen this sort of thing before, amuse you to realize how such things might come about. And here's a surface whose boundary is a knot. That knot, the boundary edge of that surface is actually a trefoil knot. It's a different version of the trefoil knot. But the surface has curves on it. And you can set up what amounts to a basis of curves on that surface, and then watch how they link one another if you push them up and down a little bit. and you get a bunch of linking numbers between those curves. And that matrix of linking numbers can then be used to compute what I've called the signature of the knot. So sometimes topological invariants are made up out of rather concrete things like that, surface that bounds the knot and other things put together. And the surfaces that bound the knot turn out to be very useful for lots of reasons, and you'll see that in a moment. Seifert in the 1930s showed that any knot whatsoever bounded a surface, an orientable surface. And his method was as follows. You take the diagram of the knot and you smooth the crossings. So this is not reconnection. It's just replacing the crossing by two parallel lines going in the same direction. And you get a bunch of circles. And then you put a disk on each one of those circles. Now, in order to do that, you might have to nest them in three-dimensional space. The innermost circle I shaded in. The next one out, I shaded it, but it has to continue to form a disk and come up over the top like a dome. And then you put twisted bands in between the circles where the crossings were, and you get a surface. So there is the architecture of this surface. And there's another way to see the appearance of this surface when we're thinking about reconnection. Because remember, when we were reconnecting, we saw that we could go up to a crossing in the knot diagram, and we could reconnect at the lines that were going in and out. And if we did that at every crossing, just systematically, we would get the Seifert circles with some little curlicues on them, but it's really the Seifert circles. And so what happened was that we went through the world line of those reconnections, and we ended up with a disjoint union of circles. And then if we imagine bounding those circles off into four space, then we would have a surface in four space whose boundary was the knot in three space. And so that shows you that at the very least, the genus of the Seifert surface is good enough to get a bounding into the four ball. But you can do better very often. You can get a lower genus than that. Okay? But we'll see that this is important for thinking about the reconnection, exactly because you can always reconnect it to something simple by doing what I just showed you. So it turns out that the genus of the Seifert spanning surface, twice the genus of the Seifert spanning surface, is equal to the number of crossings in the diagram minus the number of Seifert circuits plus 1. Now, in the case of this one, you see that I had I have 3 crossings. I have 2 Seifert circuits. 3 and 1 is 4 minus 2 is 2, and divide by 2, 1, genus 1. And genus 1 means that there would be one hole in the surface if I wrote it as an honest surface. It would be a torus. Be a torus with a hole punctured in it where the knot occurred. And that's what this guy is down in the bottom. You have to do some pushing around to see that that actually looks like a torus. But you might believe my formula. It's a very nice formula. The total number of crossings minus the number of Seifert circuits plus 1. We'll see it coming up. So, so then here's a theorem using a gun. The theorem is this, that if you have a positive link, and that means that all of the crossings are positive in the sense that if you look at a crossing in the link, you will see an oriented line and another oriented line. And then you can say, did I have to turn one of those lines clockwise or counterclockwise to meet the other one? And if the over one meets the under one by a counterclockwise turn, then it's said to be positive. So I'll show you an example of positive in a moment, just for the sake of, oops. Sorry, I won't. I'll get to an example in a moment. But the point is that we happen to know by using a certain amount of machinery, covanophthalmology and so on, that the four-ball genus of a positive link is equal to the genus of the Seifert spanning surface. So it's right there. It doesn't get simplified. It requires all of that. And so that says that the reconnection number is greater than or equal to that number I just told you, C of k minus S of k plus 1. This we happen to know by some theory. But I claim it's actually equal to it. And that part I can show you how it works. Now, the question is, I don't want to go into the details of that. And something went awry here. I'm sorry. So pardon me, but something went awry in the organization of the slides. How did that happen? Yes. Ah, there we go. Okay. So here's an example. This is a positive knot. Now you see, if you looked at any one of the crossings and put your fingers in the direction of the overcrossing line, your thumb would be pointing in the direction of the undercrossing line. So they're all the same orientation. And that's what I mean by positive. And as you see, if you believe me, it's knotted. Well, it is not. And over on the right, I've drawn all the Seifert circles, right? And we know that we can get over there by doing reconnections on every single crossing. But I don't have to go all the way over there in order to do, oh, I am not tied to anything, yeah. I don't have to go all the way over there to get an unknotted, an unlinked, unknotted, in fact, entity. Because if you think of these circles, they have some little curlicues on them from my setup, right? But those are not very serious. If I had left these connected to one another, then I would have one big circle that went around, and then it went around, and then it went around in there and in there. And I haven't created anything complicated. I'm just putting them in the form of like a tree, a droplet connected to another droplet, connected to another droplet, and finally connected to the largest droplet on the top. And it will remain unknotted. So I didn't need to use this one, this one, this one, and this one. And I can always chain them like that to get a set that I don't need to use. And the number of ones that I do not need to use is exactly equal to one less than the number of Seifert circles, right? In this case, there are 1, 2, 3, 4, 5 Seifert circles and 1, 2, 3, 4 connections that put them all together into one loop. So what I've done over here is illustrate the whole thing where I did not do any connection here. I didn't do any reconnection here, 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 or here. And I did the reconnections on the other parts. And then you have to look at this very carefully to see that indeed it's unknotted, but it is. You go down to this last part here and it just untwists. And then the next part untwists and so on. So what was the number of reconnections that I needed to do? I needed to do the number of crossings minus the number of Seifert circles minus 1, which is minus the number of Seifert circles plus 1. And that was twice the genus of the Seifert surface. So that tells us that indeed, by Rasmussen's result, if you have a positive knot, then the reconnection number of that positive knot is equal to the number of crossings minus the number of Seifert circles plus one. And so we know the reconnection numbers for a big infinite class of knots in that way. And I think that's interesting, and I hope that gets us back to doing more computer experiments with differential equation, because now we know what the answers are for lots of inputs, and we could try to see what happens in the quasi-physical evolutions and whether they come near or far from the topological answers. So that's a bit of interaction between theoretical kind of topology and this kind of computational thing. This is another example. We needn't look at it. Torus knot is a nice example to do the same way. Here, I have a torus knot of type 4-3, and you see that if I smoothed all these crossings, I would get 3 Seifert circles, a big one and another one and another one. And in general, you can do the counts and you will find that you get that the C of k minus S of k plus 1 is p minus 1 times q minus 1, so that the genus of the Seifert surface is p minus 1 times q minus 1 over 2. And this invariant of Rasmussen's that proves that the 4-ball genus of a torus knot is in fact equal to this was a very nice happening, because it had already been proved some years before that the 4-ball genus of torus knots was this way, and that was conjectured by John Milner many years before that. But the original proof, due to Kronheimer and Moravka, used a lot of gauge theory and analytical things, and this proof uses combinatorial topology of the kind that I've been sort of hinting at, but it doesn't use more complicated things. So this calculation I'm showing you is related to those things as well. Right. Let's see how we're doing. I think we could do another 10 minutes or so, yes? Now, I wanted to tell you a little about a generalization of this. Let me find it. There we go. There's a version of knot theory, which I don't know how to make it into a version that would be related to the vortices, but maybe. In this version of knot theory, one is thinking about knots that are winding on a surface, okay? So like your clothing has all this weaving, winding on the surface of your body. And here I have a torus, and the knot is winding on the surface of that torus and weaving on it. So this is an honest crossing like that. In other words, I'm embedding the knot in a thickened surface. And then you can try to understand these knots in thickened surfaces by looking at their projections into a plane. And then you get some extra crossings, because you see this guy here and the guy that went underneath and around, he's not a real crossing, so I call it a virtual crossing. And then it turns out that you can work on this knot theory by using diagrams like that instead of working with the full complexity of the surfaces. But sometimes you actually do want to work with the complexity of the surfaces. So I just wanted to give you a hint about what this kind of knot theory looks like. So if you want to be systematic about it, you can think of it this way. So when I draw a diagram and you see a little circle cross like that, it means that I'm actually on a surface and there's a little handle attached to the plane, and it goes like that. Okay? So then you can read my diagrams. See, if I drew a diagram like this and I said I'm looking at this virtual knot, then you know that I mean that I'm actually in a torus, and you have this part of the torus which is flattened out into a plane, and then there's this part which is a little handle, and this part has the knot detouring up over the handle like that. Now, if you had a couple of handles in a row like this, then you can pull on the surface a little bit up like that. And a tube will rise up as you pull on it, a tube coming from surrounding this. And you get a little tube up there like that. And if you were to remove this tube, then you would get one single handle going from one end to the other instead of the two. And so this is the main point in doing this diagrammatic theory, is that I'm going to be allowed to modify the surface if I want to and remove extra stuff. For that, I think I just wanted you to get the idea of this generalization of knot theory, because most everything I said today generalizes. And then there's the question of what would vortices be like in this domain where things are restricted to be on the surface. So here's a knot, here's a knot which is living on this surface, but it's got an extra handle in it, and the extra handle has nothing to do with that knot. So we're going to be allowing ourselves to cut that out, just remove it and put it on the smaller surface. Okay, and because I allow myself to do that, when I get to a situation like this, pull up, and here's a little extra handle, I can remove it. And that means that these extra handles can be reduced. Instead of having only one, instead of having two, I only have one, like that. And I would have one that goes all the way across two of them. And that's perhaps enough for you to see. I just wanted to give you a flavor that that these rules make a certain amount of sense, because you see, just look at this one. This is one handle over this and another handle over that, but you can think of this as a handle which starts here, goes up in the air, and comes back down over here. And if it goes up in the air and back down over here, then you can push it across and then push it down on the other side, and it becomes two little handles in sequence down there. So you can move the handles around according to very simple rules, and then you can work diagrammatically with this the way we work diagrammatically with ordinary knots. And so all of the questions about enumerating knots or finding out whether they bound surfaces in pore space and so on can be generalized to this virtual category. And in particular, what I just told you about generalizes to this category. We can generalize the topological techniques that got us the minimal genus. We can generalize the notion of reconnection, and we can talk about the reconnection number of a virtual knot, and you get the same theorem, that the reconnection of a virtual knot is equal to the number of crossings minus the number of Seifert circles plus one. So it's this virtual knot theory is an interesting generalization. Now I want to finish by going back to something concrete. This is an experiment by Professor Alexienko in Novosibirsk. And he shows that this can happen for water vortices. And his vortices are less sophisticated than Irvine and Kleckner. His vortices are coming from water vortex in a turbine. He has a turbine. It's wider at the bottom than it is at the top, and there's a motor which is causing flanges to turn, and the water is turning, and you get a vortex, and that vortex moves around. And because it's wider at the bottom than it is at the top, the vortex can move up and down a bit. And there's a nice film of his which shows it doing exactly what you see over here. The vortex comes up, comes underneath itself, undergoes reconnection, and produces a non-trivial link. So this is going backwards topologically. It isn't simplifying, it's complexifying. And this is what it looks like. We could do the film later if you're interested. I'll show it to you elsewhere on the computer, but here's the vortex going down through the turbine. And that isn't as clear on this screen as it is on my screen. If you were seeing this better, you would see this going up and around and back underneath and up there like that. Whoop. And I think you get the picture in this case. Now it's going underneath and back around like that. This is going over. And now it's coming up. And it's now in position to do a reconnection right here. See, this is going, if you put an arrow down on this, then then you'd find that this one is going up. And these can reconnect. And they get closer. And I have no detail. They just reconnect. No detail from that movie. So it's possible for the topology to get more complicated under certain circumstances. And you could wonder, of course, whether it might happen in his turbine that you would have a situation like this. It's not so far away. We'll have to see if we could get him to try to do this experiment. The one I showed you before had one curl, but if I had three in a row here, these two could come together and produce the link like he did. But then there's another one coming up in my science fiction, and it goes through here, and you'd have a trefoil knotted vortex. So in any case, the point is that it isn't just topological simplification that goes on with the vortex reconnection. And there are lots of questions. I want to try showing you a film. Let's see what happens. No, they don't have quite enough contrast here. Well, that's not bad. It's a little easier to watch, isn't it, when it's a moving picture. You saw it lop off a curve. We'll try one more and then we'll stop. Those are two where it didn't link, it just flopped off a curve. And here's the one that I was showing you bits of. It goes too fast. But that was it. The thing that's interesting here excuse me, is that when the vortices come near one another, you get interactions between them. You see those threads and filaments between them. In this case, they're just passing by. They aren't oriented in such a way that they can reconnect. But you see these filaments going on between them. And I yeah, this is worth slowing down a little bit. You see, look at what happens in this reconnection. Yes. Yeah, you can't quite see it this way. So if you're interested, we can look at it on my computer and then you can see it. But when it undergoes reconnection, there are lots of filaments that go in between one of them and the other. So it's quite fascinating to think about how would you actually model all that detail that goes on in the fluid situation. And that's enough. I'll stop here.
Thank you very much. Thank you for very visual talk. So we'll open floor for a few questions. I can actually give you a hint. In fact, Lou already alluded to this in his talk. So he carries in his pocket a rope, and I bet there are many more ropes in his bag. And all of this theory that he was describing, how things can be knotted, unknotted, can beautifully turn into magic tricks. So you can ask him to show you a magic trick with ropes. And during this workshop, during this week, he actually taught us a lot of magic tricks. So thank you for that. And any questions?
I'm an astrophysicist, so my main interest would be magnetic reconnection, which you didn't mention. So is there relevance here to solar flares, for example?
Is there a what?
Magnetic reconnection.
I don't know. I don't know about that.
Yeah, those filaments. So, I mean, I kind of understand when the direction is opposite, that the ring would be formed. I can convince myself that that is maybe a state of lower energy. But when they have the same direction, the appearance of the filaments is really, it's confusing. Do you have a reason why
right.
that happens?
So when they're in the same direction, you could look at it's hard to look at the film here, but if you look at it, they come near one another and filaments happen. And then they start coming back and the filaments sort of contract back.
What is the reason for the appearance of those filaments?
What is the meaning of them?
What is the reason? I mean,
What is the reason?
yeah.
Yeah, I don't know enough about the fluid dynamics of water to answer the question.
So that is a medium property, like it is because this is a water ring, for
It's
example.
water.
Yeah.
It's fluid dynamics of water.
Mhm.
So
Thank
you
you.
could have, yeah.
Yeah, because again,
Yeah,
I'm
yeah.
thinking of cosmic strings in the early universe. I know Luke might know more about this, but yeah, I'm interested to see if it happens in there as well. But thank you.
Yeah, I mean, I think if you think about it a while, you could probably make a simplified model of that dynamics for yourself, but worth thinking about. Back there.
This is a time of year when a lot of us are going to innocently hang loops of little lights on trees. And not very far into the approach of Christmas, these guys will get very tangled up with one another. And because they're not single, they're loops. So now the loops are tangled up. And then at the end of all this nonsense, there's a serious problem in disentangling them. And I don't know whether any of what you know about is any help to solve the Christmas light problem.
Well, as you know, as I was showing you, it's complicated to disentangle things.
Do you want to show us magic trick? Do you want to show us magic trick?
I'm sorry. Oh, magic trick. Yeah. Yeah. Just a moment. I think the knot line was sitting in the pocket, as I said. But maybe just a minute. What did I do with oh, there it is. Yes. Thanks. We'll do better with a more visible rope. Well, there are there are simple magic tricks that that any magician knows how to perform that involve knotting. For example, this rope that I'm using has some peculiar properties. It doesn't seem to hold knots very well. I mean, sometimes I just tie a knot in it and everything is fine. Yeah. And then a few moments later, I tie the same knot in it. Yeah. And it just disappears. So it's a very peculiar kind of rope. Maybe you think that that was just some sort of trick, but let's actually tie a real knot in the rope, and I'll show you it just doesn't want to stay around. Here's a figure 8 knot. And I make it more complicated like this. And it disappears. And this seems to be sort of a systematic phenomenon with this rope. I tie some square knot like that in the rope. And I make it more complicated, and I make it even more complicated. And the darn thing disappears on me. And I figure, well, maybe I just didn't make it complicated enough, so I'll try again. So I put it down through, you remember I did that. I had the square knot, and then I put this down through here. Well, maybe if I just wrapped it around a couple more times here like that, maybe that'd help. Let's see. So like that, and then through the top. Maybe that helped. Let's see. By gum, it did help. But it doesn't always help. I'll try again a little bit more simply. I'll just wind it once. It went away on me. Yeah. So this is a rather unreliable rope. But still, it's worth doing things with it. Do you ever do a chain stitch? It's a well-known stitch like this. And as you know perfectly well, this is not unknotted at this stage. I could just pull it and it will unravel, right? But it has an interesting property. It can unravel from both ends. This will now unravel from this end, and it will also unravel from this end. Maybe Werner, you could help me here. If you would just hold it somewhere along one of these ridges.
Yep.
Just like that. Now we can see that it unravels from this end, and then it unravels from this end. And now, is he holding a knot or an unknot? When I finish unraveling it, is it knotted or unknotted? Well, we'll find out. And you see, it's knotted and very obedient. It came right to him. So that's good. So the funny thing is, though, about that one is that it almost never obeys me. I'll show you. We could try to do this very same thing. There it is. And I unlock it at the other end, so it will unravel from both ends. And now, if you would help me again, this time hold the ends, but don't pull them yet. And I'll hold the ridge, and now you could pull both ends, and you see what I mean? It didn't obey me. For him, it came right over to his fingers. For me, it jumped. I don't know why. I think it just resents my manipulating it all the time. Let me see. Another rope trick that I happen to like. These are all semi-topological rope tricks. They don't involve cutting the rope or doing anything like that. This is called threading the needle. How many of you know this trick? Seen this trick before? You're supposed to thread the needle. Here's the needle. Here's the eye of the needle, and here's the thread. And I'm supposed to get through there, and that's not looking very possible, right? It looks impossible, but it isn't. It's just a matter of using the fourth dimension in the right way, and it works just fine. There are some theorems in knot theory that we all learned when we were children, but they're not true. The famous theorem in knot theory that we all learned was that if you had two knots in a row along a rope, the connected sum of two knots, that they couldn't cancel each other out unless they were each unknotted. But these are not unknotted. This is two trefoil knots. Of course, you know my rope is unreliable, but nonetheless, I claim that these could cancel each other out. The theorem really isn't right. To see that, maybe you could hold the end, and I'll show you what I discovered. I discovered that the biological field around the human arm has some special properties. So we bring the knot over my arm, and we bring the other knot over my arm, and let them interact there. Okay? But we didn't let go of the ends or anything. And if you would just take this end and hold on to it so we're not letting go of anything, then we can exhibit the fact that they just canceled each other out. And it's not just that they cancel each other out. Here they are again. It's that they did that in relation to their spin. You see, this one is spinning this way. And when we put it on my arm, the other one, we kept it spinning the same way. We put it on my arm this way. So I'll reverse the spin and let it interact on my arm that way. And if you would hold this again, then we'll see what happened to this interaction. And you see, the two knots have coalesced into one knot. And this contradicts another theorem, because this knot is prime. It isn't the connected sum of two knots, but it was the connected sum of two knots. So those theorems are gone, unfortunately. What else could I show you that I like? I just have this small collection of rope tricks that I like, and I'm hoping to expand them. But another one that I think is very nice is this one, where you make a pile of loops like this. And then you charm this pile of loops and the snake that's coming out of it and it produces for you a string of knots. Yeah.
Right? You want to try yourself?
They show you all sorts of knots and they tell you this one's really strong, it's good for this reason. This one's not really strong, it's good for this other reason. And I doubt early sailors were good mathematicians, but the strength of the knot,
Oh, the
I guess-
strength of the knot?
yeah.
That, of course, that's very interesting. There's some, by now there was a paper long ago by a man named Bayman about hitches. And then more recently, people have done some work about strength of knots experimentally and otherwise. That's that continues that. There's a certain amount of literature about it. An example in terms of strength of knot is the square knot. Let's do it between two ropes. If you splice two knots together with a square knot, then it's quite clear to everyone why it's a good splice, because each loop is grabbing the base of the other loop. So it compresses here and it compresses here. And if there's any friction at all, it works very well. If you tie that in correctly, like this, that's called the granny knot, then it can slip. You see, now it's not grabbing. The one loop is, excuse me, that it's woven under and over, so it's not grabbing at either end. And if it were slippery or just loose, then it can come apart. But the curious thing about that is that it does depend on these things depend on the configurations. So if I were to straighten one of these and keep the weave on the other, then you find that you're looking at a hitch around. Red is now a post, and this is a hitch around that post. And I think that's the clove hitch. It's a well-known hitch, and it's very good. And if you analyze it in terms of its friction in relation to the post, it's very good. So these things depend on the global configuration and the constraints. If in the case of the post doesn't move at all. In the other case, both ropes are allowed to move.
Yeah.
So
how do you think the early sailors came up with this? So that one I know is used for hanging a buoy off the side of the boat, because you can, even though there's weight on it, you can undo it from the other end.
yeah,
But yeah, I'm guessing mathematically you can prove that the knots that they call very strong are actually very difficult to
Right.
untie.
but the simplest thing that you can do mathematically is the hitches. I just wanted to illustrate it with a real post. Excuse me. So the first principle about wrapping rope around a post is this, that if you just wrap it a number of times and you add some coefficient of friction, then you're going to be raising that coefficient of friction to a power. And so it gets takes exponentially more force every time you put another wrap. So that's one principle. And the other principle is to add some extra coefficients in relation to the rope compressing the rope against the post. So if there's a crossing, then you can add another little equation for that. And you get a system of equations that are pretty reliable for figuring out how good the hitch is. And that's what Bayman did. But people have done
Yeah.
more recently other experiments involving strength of knots.
Thank you.
Yeah.
If not, let's thank Lou for wonderful demonstration. Vortices and many
Thank you.
more.
Thank you for listening to all of that.
And of course, you can ask Lou in private to show more tricks, so he knows many more. And for workshop people, we'll continue at 1:30 after quick lunch with a brief discussion session. Thank you.
Thank you.
You sail? You sail yourself?
Do I sail?
Yeah.
No, no, I don't. No.
Full on a boat. Very, very nice to meet you. I'm Venus Estate. I'm a fellow here. Hopefully I'll see you again.
Thank you.
Bye. Yeah.